What if I told you the universe is playing a game of cosmic tug-of-war, and gravity is losing? For centuries, we believed the expansion of the cosmos would slow down, pulled back by the invisible threads of gravity. But in the late 1990s, astronomers made a discovery so shocking it turned physics upside down. The universe isn't just growing, it's accelerating, stretching faster and faster into the void, as if pushed by some unseen force. This isn't science fiction. It's one of the greatest mysteries of our time, and it's rewriting the rules of reality as we know it. Picture this. You're holding a balloon covered in dots, each one representing a galaxy. Now imagine blowing air into that balloon, watching every dot drift farther apart. That's the classic analogy for cosmic expansion, but here's where it gets strange. Instead of the balloon inflating at a steady pace, imagine it suddenly starts expanding faster, as if an invisible hand is pumping it full of energy we can't see or touch. That's exactly what's happening to our universe right now. Scientists call this mysterious force dark energy, and it makes up nearly 70% of everything in existence. Yet we have no idea what it actually is. This video is your ticket to the frontier of cosmic discovery, where the answers we've found only lead to deeper questions. We'll travel from the moment Edwin Hubble first noticed galaxies fleeing away from us to the jaw-dropping observations of distant supernova that revealed the universe's accelerating heartbeat. Along the way, we'll confront theories so radical they could upend everything from Einstein's equations to the ultimate fate of the cosmos. Will space tear itself apart? Could there be other universes beyond our own? The clues are hidden in the light of dying stars, the whispers of ancient radiation, and the silent push of dark energy itself. Strap in, we're about to explore the greatest unsolved puzzle in the cosmos, and by the end, you'll never look at the night sky the same way again. To understand why the universe is accelerating now, we have to rewind all the way back to its explosive birth, the Big Bang. 13.8 billion years ago, everything we know, every galaxy, star, and atom was compressed into an unimaginably hot, dense point smaller than a single grain of sand. Then, in a fraction of a second, space itself erupted outward, stretching faster than the speed of light during a period scientists call inflation. This wasn't just expansion, it was the very fabric of reality growing at a rate so extreme, it set the stage for everything to come. But here's the twist. After that initial burst, gravity should have taken over, pulling the universe's growth into a gradual slowdown. Think of it like throwing a ball into the air. You'd expect it to rise slow and eventually fall back down. Yet when astronomers studied the afterglow of the Big Bang, the cosmic microwave background radiation, they found something baffling. This faint glow, the oldest light in the cosmos, carries tiny temperature variations that act like a cosmic fingerprint, revealing how matter clumped together in those early moments. And those patterns tell us the universe didn't just expand, it somehow kept finding ways to push against gravity's grip. The real shock came when scientists compared this ancient light to the behavior of modern galaxies. It's like finding two pages from the same book, one written in the universe's infancy, the other billions of years later, and realizing the story doesn't match. The early chapters show a cosmos where matter's gravity should have reigned in expansion, yet the latest observations prove space is stretching faster than ever. So what changed? Somewhere between then and now, an invisible force, dark energy, flipped the script, turning gravity from the universe's brakes into a bystander. The clues are etched into those ancient photons, and deciphering them might just reveal why our cosmos refuses to slow down. Dark energy is the universe's greatest vanishing act, an invisible force woven into the very fabric of empty space. Think of it like a ghostly wind relentlessly pushing galaxies apart, not by pulling or tugging, but by stretching the space between them. Unlike stars, planets, or even dark matter, dark energy doesn't clump together or gather in galaxies. It's everywhere, equally present in the vast voids between superclusters as it is in your living room right now. And here's the strangest part. The more the universe expands, the more dark energy seems to appear, as if space itself is manufacturing it on demand. This eerie behavior traces back to an idea Einstein once scribbled in his notebooks, a mathematical fudge factor he called the cosmological constant. At the time, he introduced it to explain why the universe wasn't collapsing under gravity's pull, only to later dismiss it as his greatest blunder when Hubble discovered cosmic expansion. But modern astronomers have resurrected the concept with a twist. What if Einstein was right all along, just for the wrong reason? Today, the cosmological constant is the leading explanation for dark energy, a fixed energy density embedded in space itself, never diluting, never fading. Yet mysteries remain. What if dark energy isn't constant? Some theories suggest it could grow stronger over time, or even flicker like a cosmic light switch. Imagine a universe where dark energy suddenly shuts off. Galaxies would slam together in a catastrophic big crunch. Or worse, what if it strengthens relentlessly, eventually ripping apart atoms in a big rip? To find answers, scientists are turning the universe into a laboratory. Telescopes like the Vera-C, Rubin Observatory, and the Euclid space mission are mapping billions of galaxies, searching for tiny changes in the rate of expansion over cosmic time. Even the faintest fluctuation could rewrite our understanding of reality. The stakes couldn't be higher. Dark energy isn't just some abstract puzzle. It holds the keys to the universe's ultimate fate. Will space stretch into an endless frozen silence? Or is there some hidden physics waiting to be discovered that could change everything we think we know? One thing's certain, the deeper we look, the more the cosmos refuses to follow the rules we've written for it. In 1998, two teams of astronomers pointed their telescopes at the distant universe, hunting for cosmic candles, exploding stars called Type Ia supernova. These stellar detonations have a special property. They all shine with nearly identical brightness at their peak, like light bulbs of the same wattage scattered across space. By measuring how bright they appear from Earth, scientists can calculate their distance with astonishing precision. But when researchers studied supernova billions of light years away, they noticed something impossible. These ancient explosions were fainter than they should have been, as if the fabric of space itself had stretched more than anyone predicted. The implications were staggering. If the supernova were farther away than their redshift suggested, it meant the universe hadn't just been expanding since the Big Bang, it had been accelerating, like a car pressing harder on the gas pedal over time. Gravity, the force that should have been slowing everything down, was losing its cosmic tug of war. This discovery was so revolutionary, it earned the researchers the Nobel Prize in Physics in 2011, rewriting textbooks overnight. But how do we know these supernova are reliable mile markers? Type Ia explosions occur when a dense stellar corpse called a white dwarf siphons too much material from a companion star, triggering a runaway thermonuclear blast. Because this detonation always happens at the same critical mass, the explosions are remarkably consistent, nature's own standardized candles. When astronomers compare nearby supernova to those in galaxies billions of light years away, they're effectively looking back in time, seeing the universe at different stages of its life. And the message written in that starlight is clear. The cosmos isn't just growing, it's sprinting. Today, telescopes like the James Webb Space Telescope and next-generation observatories are scanning the skies for more of these cosmic explosions, refining our map of the universe's expansion with unprecedented detail. Some supernova appear slightly brighter or dimmer than expected, hinting at variations in dark energy's push across cosmic history. Others might reveal whether dark energy is truly constant, or if it's evolving, subtly changing the rules of the game as the universe ages. Every new supernova is a time capsule carrying secrets from the depths of space and the dawn of time. And as we collect more of these stellar fingerprints, we edge closer to answering the biggest question of all: what's driving the universe to flee from itself? Even the universe can't seem to agree with itself. When astronomers measure how fast space is expanding today, they get two different answers, and the gap between them is widening into one of cosmology's most urgent mysteries. It's called the Hubble Tension, and it's like trying to solve a cosmic math problem where every calculator gives a different result. On one side, we have meticulous observations of nearby stars and galaxies, revealing an expansion rate around 73 kilometers per second per megaparsec. But when scientists study the afterglow of the Big Bang, the cosmic microwave background, those ancient photons insist the number should be closer to 67. That 6-kilometer gap might seem small, but in the precise world of astrophysics, it's a screaming red flag. So where does this mismatch come from? One possibility is that our cosmic rulers are broken. Local measurements rely on pulsating stars called Cepheid variables and those reliable type Ia supernova we discussed earlier. But what if these standard candles aren't as consistent as we thought? The James Webb Space Telescope recently scrutinized Cepheids in stunning detail, ruling out many measurement errors, yet the tension persists. Meanwhile, early universe data from missions like Planck is equally robust, grounded in the physics of primordial plasma. Both methods are meticulous, both seem correct, and yet they stubbornly disagree. This isn't just academic quibbling. The Hubble tension could be a crack in the foundation of modern cosmology, hinting at forces or particles we've never detected. Maybe dark energy isn't constant after all. Perhaps it's evolved over time, subtly altering the expansion rate. Or could there be a shadowy sibling to dark matter, tweaking gravity in ways we don't yet understand? Some theorists even speculate about early dark energy, a burst of repulsive force in the universe's infancy that left fingerprints we're only now deciphering. The plot thickens with JWST discovery of impossibly mature galaxies in the young cosmos, vast, structured systems that shouldn't exist so soon after the Big Bang. These cosmic toddlers brimming with stars suggest the early universe might have expanded faster than we thought, throwing another wrench into our models. Each new observation tightens the screws on the Hubble tension, forcing scientists to ask, are we missing a fundamental law of physics, or is the universe deliberately hiding its secrets, leaving breadcrumbs that lead us deeper into the unknown? One thing's certain: solving this puzzle won't just resolve a number, it could rewrite the story of everything. Here's the cosmic irony: the emptiest places in the universe might hold the key to its expansion. Quantum physics tells us that what we call empty space is anything but, even in a perfect vacuum where every atom and particle has been removed, the fabric of reality crackles with energy. Virtual particles flicker into existence for fleeting moments, borrowing energy from nothingness before vanishing again. This quantum foam isn't just theoretical, it's been measured in labs, with real effects like the Casimir force, where two metal plates placed incredibly close together feel an invisible push from these ghostly particles. Now here's where things get wild. Some scientists propose that this vacuum energy, the seething activity of empty space, could be the engine behind dark energy. If you add up all these tiny quantum fluctuations across the cosmos, you'd expect them to generate a repulsive force stretching space apart. But when physicists crunch the numbers, the result is absurd. The calculated energy exceeds observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the largest discrepancy in all of science. It's as if you predicted a gentle breeze but got a hurricane capable of shredding the universe. This colossal mismatch isn't just embarrassing, it's a glaring signpost pointing to something fundamental we're missing. Maybe quantum mechanics and gravity, the two pillars of modern physics, don't play by the same rules when they meet at the universe's smallest scales. Or perhaps vacuum energy isn't uniform but cancels itself out in ways we haven't discovered. Some theorists even suggest that dark energy isn't a constant force, but an echo of quantum fields shifting over cosmic time. The stakes couldn't be higher. If we crack this puzzle, we might finally understand why empty space pushes galaxies apart and whether that push will last forever. Experiments like the Large Hadron Collider are probing higher energies, hunting for particles or forces that could bridge the gap between quantum weirdness and cosmic expansion. Meanwhile, telescopes scan the heavens for clues in the distribution of galaxies or the faint ripples of gravitational waves. Every observation, every calculation brings us closer to answering the ultimate question. Is dark energy the hum of quantum nothingness or something even stranger lurking in the void? One thing's certain, the universe's greatest mystery isn't hiding in distant galaxies or black holes. It's woven into the fabric of nothingness itself, waiting to be unraveled. The universe is racing toward an ending we can't yet predict, but the possibilities are as breathtaking as they are terrifying. Picture a cosmic hourglass, its sands counting down to one of three fates. The first, and currently most likely, is the Big Freeze, a slow, silent surrender to darkness. As expansion accelerates, galaxies will drift so far apart that their light can no longer bridge the gaps. Stars will burn out, black holes will evaporate, and space will stretch into an endless, frozen wasteland where even time loses meaning. It's not an explosive end, but a whisper fading into absolute zero. Then there's the nightmare scenario, the Big Rip. If dark energy grows stronger over time, becoming more aggressive as space expands, it could eventually overpower every force holding the universe together. First, galaxies would tear apart, then solar systems, then planets. Finally, in the last fractions of a second, atoms themselves would be shredded into particles too far apart to ever interact again. Space itself would disintegrate, leaving behind a fragmented void where nothing could ever exist again. But there's a third, almost poetic alternative, the Big Crunch. Imagine the universe reversing its expansion, collapsing back into the singularity from which it began. Galaxies would rush toward one another, temperatures would soar, and all matter would compress into an inferno of unimaginable density. Some theories suggest this could trigger a new Big Bang, an endless cycle of cosmic death and rebirth. Right now, the data points toward the Big Freeze. Measurements of distant supernova and the cosmic microwave background suggest dark energy's push is steady, not strengthening, but we've been wrong before. If dark energy behaves differently than we think, if it's not a constant force but one that fluctuates, everything changes. Some models even propose it could switch from repulsive to attractive, flipping the universe's fate like a coin toss. The stakes couldn't be higher. Every observation, from the faint glow of ancient supernova to the quantum vibrations of empty space, is a clue in this cosmic detective story. And the verdict won't just tell us how the universe ends, it'll reveal what dark energy truly is. and whether the laws of physics as we know them are complete. One day, the answer might stare back at us from a telescope's lens, hidden in the light of a dying star or the whisper of radiation from the edge of time. Until then, the universe keeps its secrets close, racing toward a destiny we're only beginning to glimpse.